I've always been fascinated by the quest for a theory of everything, and superstring theory might just be the key to unlocking that cosmic puzzle. As we embark on this journey through the fabric of reality, prepare to have your mind stretched like a rubber band, or should I say, a cosmic string. We're about to dive into a world where particles aren't just points, but vibrating threads of energy that dance to the tune of the universe. And let me tell you, it's gonna be one wild ride. Now, let's consider the fundamental building blocks of our universe. For decades, we've thought of particles as tiny, dimensionless points. But what if these particles were actually minuscule, vibrating strings of energy? Imagine, if you will, that you're looking at a guitar string. When you pluck it, it vibrates and produces a note. In superstring theory, the fundamental particles of our universe are like those guitar strings, except they're unimaginably small. We're talking about a billion times smaller than an atomic nucleus. And just as different vibrations of a guitar string produce different notes, different vibrations of these cosmic strings produce different particles. Mind-blowing, right? The universe reveals its secrets in the most unexpected ways. In superstring theory, everything in the universe, from the electrons in your body to the photons lighting up distant stars, is a result of these tiny strings vibrating in different ways. It's like the universe is a grand symphony, and particles are the notes played by these cosmic instruments. Can you hear the music of the spheres? But here's where it gets even more mind-bending. These strings can be open, with free ends, or closed, forming tiny loops. Open strings might give rise to particles like quarks, while closed strings could be responsible for force-carrying particles like the graviton, the hypothetical particle that mediates gravity. Now hold on to your hats, because we're about to venture into extra dimensions. You see, for superstring theory to work mathematically, our universe needs more than the 4 dimensions we're familiar with. 3 of space and 1 of time. In fact, most versions of string theory require 10 or 11 dimensions. I know, it sounds crazy, right? But bear with me, folks, these extra dimensions aren't something we can see or touch. They're curled up, incredibly tiny, and hidden from our everyday experience. Imagine an ant walking along a tightrope. To the ant, the rope looks one-dimensional, just a line. But we can see that the rope actually has a second dimension, its circular cross-section. The extra dimensions in string theory are like that, but on a much smaller scale. It's enough to make your brain do somersaults. In the mid-1990s, physicists realized that the 5 different versions of string theory were actually just different aspects of a single, more comprehensive framework. This unified theory was dubbed M-theory, with the M standing for, well, that's still up for debate. M-theory introduced the concept of brains, not the kind you find in your head, but short for membranes. These are multidimensional objects that can interact with strings. In this theory, our entire universe might be a 3-dimensional brain floating in a higher dimensional space. It's like we're living on a cosmic sheet of paper in a much larger book of reality. Are you still with me? Because this is where things get really trippy. Let's turn our attention to one of the most enigmatic objects in the universe, black holes. These cosmic behemoths have long puzzled physicists, especially when it comes to reconciling them with quantum mechanics. But string theory? It might just have some answers. In the string theory framework, black holes aren't just empty voids of nothingness. They're incredibly dense collections of strings. String theory suggests that this entropy comes from the many different ways strings can be arranged inside a black hole. It's like trying to count the number of ways you can tie your shoelaces, but on a cosmic scale. And let me tell you, that's a lot of ways. This stringy perspective has led to some fascinating insights. For instance, it's helped explain the origin of black hole entropy, which is related to the number of possible internal states a black hole can have. Now, I'll be the first to admit that the math behind string theory is, well, it's not for the faint of heart. We're talking about some of the most advanced mathematics ever developed. One of the most fascinating aspects of string theory math is something called duality. This is the idea that seemingly different physical descriptions can actually represent the same underlying reality. It's a bit like looking at an object from different angles. The views might seem distinct, but they're all describing the same thing. This concept has led to profound insights not just in physics, but in pure mathematics as well. It's enough to make even the most hardened mathematician weak at the knees. The beauty of this math is that it reveals connections we never knew existed. It's like discovering that different musical instruments, each beautiful in its own